We're going to take a look at a free response question from the 2017 AP exam. And while we've seen all of the ideas in this problem, it's presented in a slightly different way. And I thought it would be worth our looking at this because they also asked questions in this style back in 2011, 2012, and just last year in 2019. Before going on, please pause this video and read through the free response question that's posted on Google Classroom so you get a sense of what's going on in this problem. This is all about dealing with a differential equation, but this time, rather than just our usual dy dx equals stuff, it's a differential equation with some context here. H of t tells us the temperature of the potato, and t is the time in minutes. The temperature is changing at a rate given by this particular differential equation. One thing you should realize about it is there is no t over here. Doesn't matter, we can still use all of our separation of variables ideas and stuff, but we're going to have to deal with this a little bit differently. In letter A, we're asked to write an equation for a line tangent to h of t at t equals 0, and then use it to do an approximation. Well, whenever I see tangent line, I always start from y minus y1 equals m times x minus x1. However, there isn't an x and y in this problem. Instead, there's h's and t's. H is in the place of our y. H is our dependent variable, and t is in the place of x. T is our independent variable. So instead of using x's and y's, I'm going to use t's in place of x and h's in place of y to say h minus h1 equals m times t minus t1. By the way, we were also told that h of 0 equals 91. Well, actually, that h of 0 equals 91 gives me my t1 and my h1. I know that at time 0, the temperature of the potato is 91 degrees Celsius. Then I just need to find my slope. I just need to find h prime of 0. Which means plugging in a 0 where the t is, but I can't really do that. I don't really have a t over here in my formula. You know what? Rather than saying h of 0, why don't I talk about this instead of finding dh dt at the point 0, 91, when t is 0 and when h is 91, which I just got from that initial condition over there. Well, this one I can handle. There is no place for me to plug in the 0 because there was no t, but there is a place for me to plug in the 91, the h. I'm going to get negative 1/4 times 91 minus 27. By the way, this was a non-calculator question, so I should proceed without a calculator. 91 minus 27 is giving me, let's see, I'll change that. 11 minus 7 is 4, giving me 64. Negative 1/4 times 64 is going to give me negative 16. So my tangent line is looking like h minus 91 equals negative 16 times t minus 0. I can solve this for h and make it h equals negative 16 times t. There's no need for the minus 0. Plus 91. And that's my tangent line approximation to the solution of the differential equation. Well, next, I need to use that tangent line to approximate the temperature at time 3. h of 3 by my tangent line is approximately negative 16 times 3 plus 91. That's negative 48 plus 91. I'm going to go do the calculation on the side over here. And that's looking like, nope, that's not. 8 minus 4 is not 3, it's 4. It's looking like my final temperature is predicted to be 43 degrees Celsius after 3 minutes. That's my tangent line approximation. In part B, we're asked to use the second derivative to determine if the answer in part A was an overestimate or an underestimate. Well, before I do any of this stuff, I need to go and I need to calculate my second derivative. And I think I don't have the first derivative showing anymore, so let me just rewrite that for you. dh dt equals negative 1/4 times h minus 27. I'm going to go and do my second derivative, so I'm going to take the derivative of the first derivative. No, I don't necessarily think you have to write out the line that I'm writing out right now. But that's going to give me d squared h dt squared, my symbol for the second derivative on the left. Negative 1/4 times, well, the derivative of h, not 1, but rather dh dt, the derivative of negative 27 is just 0. So I could say my derivative is negative 1/4 times dh dt. I should write this just in terms of h's and t's, no dh dt in there. So I'm going to go and I'm going to replace my dh dt with, well, the formula that I have over here for it, negative 1/4 times h minus 27, d squared h dt squared equals 1/16 times h minus 27. But that's only the first part of letter B. Then I need to figure out, is this second derivative positive, negative, things like that. Well, we were told in the problem that the temperature of the potato is always greater than 27 degrees Celsius. In case you missed it, right over here, the temperature of the potato is always greater than 27 degrees Celsius. Well, if h is greater than 27, I know that this thing over here is always going to be positive. Again, the logic here is h is something greater than 27. No matter what you plug in that's greater than 27, this thing over here is positive, times 1/16 gives you a positive final answer. If the second derivative is positive, that means our graph is concave up. Well, if we have any sort of concave up function, our tangent line approximation, whether it be there, or here, or wherever, is always less than the function itself. That was one of the things in that salmon-colored pocket. If you go to the page about overestimates and underestimates, we can use the concavity to determine if a tangent line is an overestimate or an underestimate. Because my tangent line is an underestimate, well, what I got in part A is an underestimate for the temperature. To finish off this logic, I'm going to say, because d squared h dt squared is positive whenever h is greater than 27, which we were told in this problem, our solution curve is concave up, so a tangent line approximation to it must be an underestimate. I don't think this is a rule that you need to memorize, but I think you need to realize that we use concavity to determine if tangent lines are overestimates or underestimates. Draw in something with your particular concavity. In this case, I'm concave up. I drew in a couple tangent lines, and I saw that those were all completely underneath your concave up function. In part C, well, normally with these problems, the part C would involve solving our particular differential equation over here, which I could solve by separation of variables. However, in this case, we were given a slightly different differential equation that we need to solve to finish this problem off. We're told, nope, you can't see that. We're told in part C that an alternate definition for the differential equation would be dg dt equals negative g minus 27 to the 2/3. We're told that g of 0 equals 91. And we're asked to, so g is our temperature, t is our time. We're asked to solve this differential equation and then use it to find the temperature of the potato, the actual temperature of the potato, at time t equals 3. I'm going to start by separating my variables. Realize that you don't have a t, but that's okay. I'm going to divide both sides by the g minus 27 to the 2/3, and I'm going to leave this negative 1 with my dt. I'm going to get dg over g minus 27 to the 2/3 equals negative 1 dt. I'm then going to integrate both sides. Now on the left, if it was just dg over g minus 27 to the first, that would be my case where I get natural logs. I do a u substitution, get natural logs and all that stuff. In this case, though, because my power is a 2/3 in the denominator rather than a 1 in the denominator, this is just going to be a power rule sort of problem, although I will still have to do a u substitution. There was no need for me rewriting that over there. What I meant to rewrite was the integral of g minus 27 to the negative 2/3 dg equals the integral of negative 1 dt. On the left side, I need a u substitution. I'm going to say that u equals g minus 27 and du is dg. I'm going to get the integral of u to the negative 2/3 du equals the integral of negative 1 dt. I'm going to go and integrate both sides. I'm going to get u to the 1/3 over 1/3 equals negative 1t plus a constant. That's 3 times, I'll replace the u with g minus 27, so 3 times g minus 27 to the 1/3 equals negative 1t plus c. I need to do a little bit of work to solve this thing for g, so I'm going to divide both sides by 3. Might as well come up over here. I'm going to get g minus 27 to the 1/3 equals negative 1/3 t plus, I'm just going to say a constant because a constant divided by 3 is still just a constant. Going to get rid of my 1/3 power by raising both sides to the 3rd power, to the reciprocal power. So g minus 27 equals negative 1/3 t plus c to the 3rd. Add 27 to both sides. And my general solution to the differential equation is g of t equals negative 1/3 t plus a constant to the 3rd plus 27. I need to deal with my initial condition, though. I was told, just like in part A, that the initial temperature of the potato is 91 degrees. I'm going to plug in a 0 and set it equal to 91. So 91 equals 0 plus c cubed plus 27. I'll go and subtract 27 from both sides. 64 equals c cubed. Take the cube root of both sides. C is going to equal 4. So my solution is g of t equals negative 1/3 t, it's a negative, plus 4 cubed plus 27. I'm going to rewrite that in case you just couldn't see the negative there. G of t equals negative 1/3 t plus 4 cubed plus 27. But I'm not done. I was asked to find the temperature of the potato at time 3. Same thing I was doing in part A, but in part A I was using a tangent line approximation. In part C I'm using the solution to a differential equation to get my temperature. G of 3 is going to be negative 1/3 times 3 plus 4 cubed plus 27. This is negative 1 plus 4 cubed plus 27. That is 3 cubed plus 27. That's 27 plus 27. And here, I think, I just want to make sure, yep, I'm getting an approximation of 54 degrees Celsius. The reason I wanted you to see this is I wanted you to see with how we deal with differential equation stuff when there's some sort of context here, and also when it seems like there's some variables missing and all of that. I do want to quickly just go through how this was scored on the AP exam. This was a very low scoring question. The mean was 1.54 out of 9. Part A was worth 3 points. 1 point for getting that slope of negative 16. 1 point for being able to write the tangent line, y equals 91 minus 16t, or h equals 91 minus 16t. 1 point for plugging in your 3 and getting your approximation to be 43 degrees Celsius. Part B, even though it was complicated, it was only worth 1 point, so that was kind of nice. But the 1 point took care of everything. So 1 point for saying that it was an underestimate with a reason. It was an underestimate because your second derivative was always positive, so your graph is always concave up, so a tangent line will have to be below our function. Part C was worth 5 points. 1 point for separating your variables and saying dg over g minus 27 to the 2/3 equals -1 dt. 1 point for being able to get both of your antiderivatives. So if you got down to this line, you got 1 point. 1 point for including the plus c and using that initial condition of 0,91. They plugged in earlier. We're kind of used to plugging in at the end, so I would just continue doing the plugging at the end. 1 point for getting your equation that involves g and t. So 1 point for getting your g of t equals 27 plus, they wrote this out a little differently. We would have said 4 minus 1/3 t in parentheses cubed. Whatever, it's fine. And then 1 point for getting that function and plugging in your 3 to get your 54 degrees Celsius. I guess the first point didn't have to be a g of t function, just something with g's and t's in there, so maybe something kind of like this line over here. The final point was for solving for g and plugging in your 3. You wouldn't have gotten any points on part C if you didn't separate your variables, and if you didn't include a constant of integration, the most you could have gotten was the first 2 points, the separation part and the point for the antiderivatives. You're going to take a look at 2 similar problems from 2011 and 2012, but hopefully having looked at this one, you'll have a good idea of how to approach this. We'll then go through those on Zoom next time. Last year also included a question sort of like this, but I'll save that one for another time.